All right. Well, let me actually first start because we got this. How are we feeling about maximum likelihood estimation and logistic regression from last week? Are there questions, things that should uh, say again or try to explain in a different way? I see some nodding. Can you somebody be brave enough to maybe, is it like all of it or is it all of it? Um, so can someone help just chime in and maybe have a conversation? So when we move to the generalized linear model, do you get the idea that well, let's go back, right? When we talk about ordinary least squares, what's the key assumption? And if you did that lab, you kind of looked at it a little bit, was that the residuals are normally distributed, right? And so what the generalized linear model does is allow us to specify different distributions other than the normal distribution that our dependent variable can have, which is really handy when we have a dichotomized, 0, 1 dependent variable. The other big step is in order to estimate those models, we need a different way of fitting those lines, right? So ordinary least squares, because it's all predicated on minimizing the squared residuals, and that assumption is that those residuals are normal. Now we have a different distribution, so we have to solve that problem a little bit differently, right? So instead of trying to get the shortest essentially distance between each observation and the predicted value, right? That's the residual, that error, right? We need to use a different method, and that's what maximum likelihood estimation is, right? It's sort of an algorithmic approach in order to find a solution that minimizes some error. We just flip it. Instead of minimizing errors, we can maximize the log likelihood, right? So in the terms of like logistic regression, well, actually, let me step back. When we fit a continuous variable, that's exactly what we could do. We're just minimizing those residuals. Just instead of using a formula, we're using this algorithm. When we went to a dichotomized variable, we're saying what we're trying to we're going to take the likelihood ratio, right, which is probability of success over the probability of failure. So that gives us some value between 0 and 1. And if we take the log of that, now we're just attempting to maximize that, right? But maximizing it is actually minimizing the error, right? So let me open up the slide deck so I can look at a picture real quick. All right. I want to go. This is really the one I want to look at, right? I mean, we could look at it this way because we could solve it this way, right? So these would essentially be residuals, but in a logistic sense, right? So instead of fitting a straight line, we're fitting sort of this logistic curve. But if we take the log of that, right, we end up with these values, which is both simultaneously a computational sort of trick, but it also has sort of this ancillary benefit that it tends to fit the data a little bit better, like because you could write this, and I probably have an R script somewhere. I don't want to take the time to find it, but if I find it, I could throw it on Slack, where you solve it by trying to minimize these errors versus maximizing these log likelihoods. The curve is a little less, it just fits a little bit better in terms of generalization. A lot of times, if you just fit the errors, what the model would do is probably come right up here and then jump up very sharply and then kind of tail out. So doing this log likelihood kind of smooths it a little bit better, which is better for fitting and generalizability. But ultimately, right, what are we doing? Right, we have residuals that are now not normally distributed, right, because they're following sort of the binomial distribution here. But we're still trying to minimize that errors just through this algorithmic approach. So those are kind of the big ideas I would hope you can get away from that. So let me pause and see if you could ask some more specific questions and how you can kind of talk about that.
I think part of where my struggle is that I don't know the practicality of this. Like when would you utilize this, or like when would this be helpful, or can you describe a scenario where you might use this?
Oh yeah, I would say as you get in as you start looking at what approaches people are solving to do predictive models, logistic regression is still one of the most common models you're going to use or methods you're going to use. Um, so you're going to learn other things, sort of non-parametric methods, but logistic regression is going to be an extremely common and often the first one you're going to do, and then you're going to move on and try some other models. So uh, this is extremely common. Now you get to other things where you might have sort of a count variable as your dependent variable. Well, I won't go into it, but the model you would still use a generalized linear model. You'll still use the GLM function if you're in R, but the family is going to now be Poisson, right? So Poisson's just a different distribution that that describes count data better, right? Binomial distributions, if you go way back to the probability, are really good distributions to describe sort of dichotomized or probability distributions, right? And then of course we talk a lot about the normal distribution when we have a continuous variable, right? So that's, this is sort of that first step that allows us to sort of fit models, any model that doesn't fit into the normal distribution. So let me, there's one other, oh no, I don't know what's going on here. There we go. So let me see here. How do I Google this? Relationship of statistical. Don't judge my spelling as I'm trying to type fast. No, I spelled that wrong. Let me do interactive because there's an interactive. I thought I might have had it linked in the course website, but it'll probably be quicker find it this way. This is it, but there's a better one. Oh, maybe it is on Wikipedia. I mean, this is it, but there's somebody has one that as you hover over, I'll try one more link. Oh no, I guess not.
So generally for non-normally distributed data, this is what you would want to use as opposed to an LM function.
Yes. Yep. LM will only fit will only fit sort of the ordinary least squares model. That's all it will do. So you don't ever want to use LM with a dichotomized dependent variable. That would not be appropriate. So you got to move to the generalized linear model. Now it's handy. I mean, the LM function is handy for lots of other reasons. And it's also just a stepping stone, right? So so this is not exactly the one I'm looking for, but you could start at the normal, and there's better ones because I can't, it's really tiny on my screen. There's one that tells you what the relationship is. So I'm trying to see, oh, here it is. Right, so if you start with the normal, but if you have a dichotomized outcome, you go to the, you could go to a logit normal, or there should be a binomial. Here's the binomials, right? If you have, here's a chi-squared. If your data is, sort of count or cell data, right? So counts or contingency tables, right? You would go that way. Where's the Poisson? That's another common one that you occasionally encounter in, statistics, but there's, I'll find it, post it on Slack, but there's sort of ways that these parameters change, and that's kind of helpful. But quite frankly, what you're going to do in practice, what I hope you get out of this, out of last week's lecture and doing the lab, and is at least some comfort in running the logistic regressions and then interpreting, the outcomes, and then you're going to encounter, say, like I said, I told you Poisson, so you got a head start. But this is what I do. Is like, here's what my data looks like. It's has this kind of distribution, or I think it has this, and I Google it and it says, oh, for that kind of data, you would use this. But like I said, logistic and just the normal, which is the default in the GLM, is what you're going to use. So if we go to our studio, let's sign in. So really, all I want to do is pull up the help documentation for the GLM function. Here we go. All right, so right, so you have this family. So Gaussian is just another word for the normal distribution. I think I might have used that phrase once when on the slide where I presented the functional form of the normal distribution. So Gaussian is just the normal. And if you go down and look in the family, I think you had there's a family function. So you can see, so binomial is the one we've been using, but you could, Gaussian is sort of the default, but here's like the Poisson, and then you have quasi-binomial and Poisson. Those are just special cases. If you have large data sets, occasionally, this came up, I think, last week. I think it might have been Greg that asked, or Andrew, I can't remember who asked. Could you just get into, find yourself in a local minimum? And with certain complex data sets, it is possible that the maximum likelihood estimation won't find a solution. So a couple things you could do is change your starting point, right? And kind of give the algorithm a hint. The other is there are these quasi distributions that often can be used to avoid those pitfalls where you get an unsolvable or a lack of a solution, and that would nudge you along. But that's sort of very advanced stuff and very unusual circumstances that you would encounter. So long-winded answer, Christian, but logistic regression is something you're going to use quite a bit as a data scientist and in this program. It's sort of one of the first steps because it's pretty straightforward and generally easy to understand. May or may not result in the best performance, particularly if you're trying to do new predictions, but it is like in Angela and I's world, we have to, we're often balancing prediction accuracy to explainability. Like when we talk about our results and just saying, well, adding this increases the accuracy is often insufficient to social scientists. They're like, but we want to know what variables are related to that. So things like random forest that you'll probably learn maybe next semester tends to perform better than logistic regression, but it is much more difficult to explain how you got to that answer. Like it's these variables that are, kind of more significant predictors than these other variables, because you're literally building thousands potentially of submodels and sort of taking this vote. Now, when you get there, there's a great package called Random Forest Explainer that helps, but it's still a challenge to explain it. All right, let me please throw questions in the chat. We can come back to it. I don't think this is a long slide deck. I'm going to actually save the predictive modeling slide part that's in the logistic regression slide deck from last week. I'm going to save that until after Thanksgiving. So we won't have class next week because it's the day before Thanksgiving. So I guess it'll be 2 weeks. We'll do a little bit on the predictive modeling, which is really just about changing our points of view, because we're going to talk about R-squared tonight. And that's going to kind of shift it. And then we'll do a very, very brief kind of introduction to Bayesian model, just to kind of mostly to contrast it to what we've been doing all semester, which would be considered the frequentist approach. So that's our plan for I think the remainder of the semester. So we are almost at the end. And we usually do this before logistic regression. So this is kind of an interesting little experiment for us. So as we go through this, maybe this will help looking at the logistic regression, the GLM results as we go forward. So we're going to walk through an example. This is just a simple little toy example, but hopefully easy to kind of see what's going on. And what we want to do is estimate the weight of books based upon their volume, area, and their cover type, right? So we got a couple of variables. So we could just start and do our simple LM, right? So where we want to model weight from volume, right? And we can get, if we run that through the LM function, we get an intercept of 108 and a slope of 0.71. We can draw it here and we get an R-squared of 80%, right? Nothing terribly new here. And here's the summary of the LM output. We may come back to that in a second. But if we want to bring in sort of, we could look at the difference between hardcover and paperback books. And so probably there's some natural intuition, right? Hardcover books tend to weigh more than paperback books of roughly the same, volume. And if we plot that as a scatter plot, so all I've done here is color code and kind of change the shape of the point so that these reddish circles are hardback books and these greenish triangles are the paperback books. So we could just kind of do our best, try to draw a line here. And I would say maybe I would draw a line from paperbacks kind of down here, but my hardback books might be a little bit higher. So we want to account for that other variable. We kind of looked at another example similar to this, where we estimated two separate regression models, and like by separating them, I think on sex, we found that the R squared of the separate models were greater than if I just did them all together. What we want to do now is kind of bring them together. We don't want to estimate separate models for every different category that we might have. Okay, so it's pretty simple, right, to do in R, because we're just going to add. So we have volume, and we're just adding this plus sign, cover, and so R just gives us this output, right? But now we have sort of two rows in our outcome, and there's been some things here I've been sort of deliberately ignoring: the t statistic and this p-value for each row. Because when we just do a bivariate regression, and bivariate, I mean we have one predictor or one independent variable and one dependent variable. These aren't terribly important in that situation. But now they're going to become a little bit more important. The other thing we're going to notice is that we have this multiple R squared that we've been reporting, but we also have this adjusted R squared. And we're going to need to talk about what that is and what that's about. All right, in terms of, I think I might have showed this before, but let me find that app. So Shiny Apps. Size, I think this is it. Nope, wrong app. Yeah, this is it. Sorry. Yeah, okay. So if I do two numerical independent variables, I want to look at the plot, right? So when we move to a multiple regression, we are in a lot of ways doing the same thing. We're still minimizing the sums of squared residuals. We're just doing it in three-dimensional space so that we can kind of estimate this plane, right? So we have two predictors, right? And we're trying to minimize the distance as we move vertically. So the error is, sort of that vertical line from the positive in affect and anxiety severity in this particular example to the depression. So if we project each of these points to that plane, that's the residual, right? So, and then if you add a third, if you can think in four-dimensional space, if you're Dr. Strange, maybe that makes sense to you, but in principle, that's kind of what we're trying to do. Okay, so we can write this out like this. So we still have an intercept, right? We always have to have an intercept. So we have a slope for the volume variable, and we have a slope for the cover. But in this case, right, cover is just a categorical variable. And so I want you to pay attention here. So we have cover PB. So what R did for us automatically here is something called dummy code the variable. So we can represent categorical variables as quantitative variables by creating a matrix where we have just 0 and 1s. So with one category, right, what we do is we have a variable, and if it's 0, it's a hardcover book, and if it's 1, it's paperback, right? So we don't see hardcover in this output because you're only going to have that. So if we had 3 categories, let me get my drawing tool here real quick. So if we had some variable, and right, it could be A, it could be B, or it could be C, right? We could dummy code this as saying, we could say A and B, right? And what we're going to do here is say this will be a 1 if it's equal to A, otherwise it'll be a 0. So we go to this one, this would be 0, and this would be 0. but then over here we would have 0, 1, 0, right? So with just two variables of 0 and 1s, we can represent every combination of three variables. If we had four categories, we would need three columns, right, to do that. And so the one that is 0, 0, right, in this case, that's often referred to as the reference group, because what we're going to see is these variables are 1 when this is 0. So as we go from 0 to 1, so that's the category that's not represented. So what ends up happening, and how do I clear everything here? All drawings, and then I want to go back to my mouse. Okay. So as we add other, other categories, there's always going to be one category that's not going to be represented here. And there's no, sort of rule on how you do it. You could just let R do the dummy coding. It doesn't matter in terms of like R squared or things like that. It only matters sometimes in interpretations. The sort of easiest thing to do is just take the category that has the largest observations and make that the reference group, so that the comparisons are to sort of the major group. But it doesn't, the model fit is going to be the same regardless. All right, so let's look at it in this example. So what we're saying is, for hardcover books, what we're going to do is plug 0 in for the cover, right? And so we could simplify the formula to a simple bivariate regression. So this is essentially the bivariate for hardcovers, and then here's the bivariate regression for paperback books. So we just put a 1 in for this variable when it's a paperback, right? So a couple of weeks ago, we did that with sex, right? And we just had the two models, but now we have a way of sort of essentially combining those two separate regression models into a single model that we just input this other variable for. Right, and so we could visualize it this way, right? So this is all drawn from this equation, and we can see here, we see that indeed the hardback books have, on average, a slightly higher weight than the paperback books, given the same volume. All right, so slope, this slide will help you on the interpretation. So the slope, what we're saying is all else held constant, books that are 1 cubic centimeter greater in volume tend to weigh about 0.72 grams more. And then we have a slope of the cover. And so what we're saying is all held constant. The model predicts that paperback books are 184 grams less than hardcover books, right? Because we have a negative. This one happened to be coded, so paperbacks were the 1. Right. So this slope almost gives you sort of an average difference between those two groups. And then we have the intercept, which is hardcover books with no volume are expected to weigh 198 grams. Now, of course, that's nonsense, right? We've talked about this before. That's kind of interpreting beyond our data, but it's necessary in order to have the estimate. All right, let's look at a slightly more complicated example. So this is a data set that from Gelman that has a row for each state. And we have a couple of key, kind of state metrics. And what we're kind of interested in is modeling poverty, right? So this is the percent of the population of that state that lives below the poverty line. And we have some interesting variables. So we have percent that live in a metropolitan area, percent that are white, percent that are a high school graduate, and the percent that have a female head of household. And so this is, I think I created this using the GG Paris plot. This is pretty handy if you're trying to look at a lot of variables all at once. Just really quick, the main diagonal just gives you the density distribution. If you look at the documentation, you can customize this to your heart's desire. If you wanted histograms in the main diagonal, you could, but I tend to like the density. Below the main diagonal, so this is called the main diagonal in matrix, it kind of comes from matrix algebra stuff. Below that diagonal are just scatter plots, so we can look at the relationship between any two pair of variables. And then in the upper here we have just the correlation. So we could see that poverty and percent living in metropolitan is correlated at negative 0.204, right? We can kind of see a little bit that here, but notice there's no stars. We are doing it is doing a null hypothesis test here. So this would be white and poverty are, is significantly correlated with P less than 0.05. Here's one high school grad and poverty is correlated with so 3 stars would be less than 0.001. Is that right, Angela? 0.0001. Yes, two zeros for 2 stars. Okay. All right, so we could just start, right? Let's model poverty from percent female household. Just do our typical bivariate regression. We end up with an R squared of 27% or so. Right, and here's just that scatter plot and just that regression. All right, but what we want to do is really look at that R squared, because all we have been doing is taking the correlation and squaring it. Right, so there's kind of 3 major ways we could do this. Right, the first is what we've been doing, taking the square of the correlation coefficient. We could also take the square of the correlation coefficient of y and y hat, right? But we tend to not know y. We only have y hat, so that's often not really helpful. But we could kind of define R squared more generally, right? We've said it's the percent variance explained, right? It's kind of what we've said, but let's be very specific. What we're saying is it's the explained variability in y, our dependent variable, over the total variability in that y. And so we can actually use ANOVA to kind of extrapolate the different components of the variation of y explained in our regression model. Now, the denominator here, the total variability of y, we learned, I think, in chapter 2. That's just the variance of y. That tells us that variability that we have there, right? Which is, remember, is the standard deviation squared. So here, I'm just going to take the LM of the poverty here. So I think this is just the bivariate. Yes, this is the bivariate, one predictor. And we can just run that through ANOVA. And you can go back to the ANOVA lecture to look at this, but remember what we're typically looking at is sums of squares of the explained parts to get to the mean squared, which we divide by the degrees of freedom to get an F statistic. Okay, so the F statistic's handy because that's going to tell us whether or not these predictors provide a significant are significant predictors of our dependent variable, which with one variable, we have here, we can look at it other ways, but we'll come back to this F value in a moment, right? So the residuals here, right? So this is the error in the model. So this is the unexplained variance, and this is the variance explained by female household, right? So, and if we sum these two, that gives us the total variability, which in this case is 480. We could also get it by actually just calculating the variance of the variable using the var function that we learned like in chapter 2 in the descriptive stats. But if you sum these up or do the var, you can satisfy yourself later, they will be the same, okay? So this 347 is the unexplained variability. So that's the sum squared residuals, which is, here we're just summing the squared of the errors, right? So that's just the residuals as we know and love them now. So then we could take the sums of the squared model, right? That's really what we're interested in. The total variability is going to be the total minus the error, which is the explained variability, which is 132, which is in the table here because we only have one predictor. And so we just take that ratio. So the 132 over the 480 gives us an R squared of 28%, which is going to be close to taking the correlation, the square of the correlation coefficient. So why bother, right? For single predictor regression, this is obviously overkill. But in multiple regression, right, we can't just take a square correlation coefficient because we have multiple correlations, right? So we want to look, and we are also very much interested in the explained variability. We want to also take into account overlapping variance explained in our dependent variable, and I'll show in just a moment. So here, if I take that data set and I'm adding white with the female household, and I run that through, so notice now we have 3 rows, right? So we always have the intercept, right? So here's the slope for female households, slope for percent white households, and we get these standard errors. And okay, so first thing I'll say, we have now these t statistics, and what these things are doing is is doing a null hypothesis test. And the null hypothesis is that the coefficient or the estimate or the slope is 0. So what we're generally hoping for is for a t-statistic large enough and a p-value small enough that we reject the null hypothesis that the estimate is something other than 0, right? So in this example, right, the female household variable is a significant predictor, but the percent white is not because the p is larger than 0.05. So this estimate from the model is not statistically significantly different than 0. Okay, we'll set that aside for just a second. So from this multiple regression model, we're going to run it through the ANOVA so we can extract the sums of squared residuals for each component. Right, so here we have the error, right, and we have the sum squared residuals for female household and percent white. So what we want to do is add these two. These are going to be the explained variance. And then we're going to add all three of these to get, all right, so the 480 is not going to change, but you can add all three. So the residuals is less than it was on this page, not by a lot, but a little bit, right? And so we end up with an R squared of 29% when we take that quotient. So really didn't go up a whole lot. And why is that, right? So there's this notion here of unique information. If we look at the relationship, we go back to this scatter plot matrix, the correlation between, so this is white and female household is negative 0.751, significant to, p less than 0.005. We look at the scatter plot, right? Each data point here is a state. There's potentially one outlier here. I don't know what state that is, but there's a very strong linear relationship, right? So think about this. If I had, we started with the female household, adding in the white is not telling us anything different than what that other variable is, because they're so strongly related. And that relationship like that in a modeling context is called collinearity. And this can be problematic in a number of instances. This is problematic if you're, well, it's certainly going to be a threat to the validity of your model. Because, when you're doing these models, you're kind of trying to find this balance between explainability and parsimony. And what I mean by parsimony is we want the simplest model that explains the most variance. Now, what I have noticed in the data science world over the last decade or so, we tend to treat predictive models a little bit more as black boxes. And in 2 weeks, I'll explain that and how metrics are done. So we often don't care about how individual variables contribute in the model. All we tend to care about is, did the overall accuracy increase? So in that context, multicollinearity is a little bit less of an issue. Sometimes should be something you should consider, but using, as we're going to see, the adjusted R squared is going to penalize you in terms of that metric as you go through, add more variables. So, when you have these multicollinearities, it's like, well, which variable do you use to explain? And so there could be kind of theoretical issues there, and there's also some model estimation issues. When you have a lot of multicollinearity, that's an instance where sort of maximum likelihood estimation might start to fall down, because then you have all these kind of local minimums. All right. So, all right. So the the two predictors said if they're highly correlated, there's collinearity. Yeah, I think I said everything on this slide. Okay, so let's look at the R squared versus adjusted R squared. Right. So when we had model 1, right, we had the R squared, which was 28%, and then the adjusted R squared was 26%. When we went to the 2 predictor model, we increased R squared by 1%, but the adjusted R squared ended up being the same at 26%. Right. In this example, that variable we added really didn't add any additional explanation in our dependent variable. Right. So one way to think about it let me get my annotation again, right? So if we have, come back, annotate, draw, right? So if we think about, right, variance. So this could be the variant, variance of y. I don't know why there's a lag in the draw here, I'm sorry. All right, so then we had, well, I'm just gonna call them x1 and x2, right? So we could say, you know, we're looking at how, like, this is the variant, this box here. Oh my God, this is frustrating. So here's the variance of x1, right? And then we had another variable that kind of accounted for more or less the same, right? And this could be, I'm just going to say x2. My trackpad is not responding, right? So there's a lot of overlap. Then all of this bit here, over here, that's that error variance. If we go back a slide. So the way to kind of conceptualize that is from this, right? So the 480 would be the area of this bigger box. The 132 is the area of this box, and the 8.2 is the area of this box that doesn't include this box, right? That's essentially what we're trying to do, because they're collinear. We're trying to get rid of that overlapping variance. All right. And this is generally how the adjusted R squared, right? So we're taking the sums of squared error over the total, right? Which is what we've been doing. And then we kind of have this penalty where N is going to be the number of observations we have, and P is going to be the number of predictors we have. So as you increase the number of predictors, there's going to be this built-in penalty. So you can kind of, so it's just this penalty, so that you really want to make sure that additional variable that you introduce is actually adding more explained variance than what this penalty is going to account for. Questions about that? So going forward, you're only going to report, let's look at the, where's my multi? Did I go by it? Did I not? I just have it in the table form. Okay, we can look at this one. So when you're looking at the LM output, and this is similar in GLM, right? You get these same kind of metrics. Well, when you use the Gaussian family, we don't have an R squared for logistic regression. We'll look at two other things in 2 weeks. But at this point, what I would say is you're only ever going to report the adjusted R squared. As in your models. Now, the last thing, kind of alluded to it, but you in the summary for the LM output, we have this F statistic, and this is doing an ANOVA, and the ANOVA is the null hypothesis that all the estimates are 0. Okay. So in general, I mean, almost always this F statistic is going to be statistically significant, because generally, if you bothered running a model, at least one of the variables are a significant predictor of your dependent variable, and as long as one of them are, then this F statistic, or the ANOVA, is going to result with an F statistic that you're going to reject the null hypothesis. So, but just so you know, it's there. In that rare case, you end up with an F statistic that has a p-value greater than 0.05, then none of your variables are really significant predictors of your outcome of interest. But because that we can use that ANOVA, it's a really convenient way of extracting out these sums of squared to find out the variance explained of each component to our dependent variable to get to the R squared. Questions?
So you might have explained this. I had to step away for just a moment, but what is the difference in how the adjusted R squared is actually doing this division here? So why doesn't it increase if the two variables are collinear?
Because
Oh yes,
well,
here we go. Sorry, that's
yeah,
what I
yeah.
missed.
So we have this part,
That's
right?
what I missed. I see.
Yep. And
Cool.
and so in this instance, if we look at I'm sorry, where's oh, that's the comparing the two models. This is the one I want, right? This 8.208, right? So the total variance is 480. So what's 8 over 480 is like 1.6%, right? So adding this variable, you know, is 1.6 of the total variance, right? Which is why the R squared went up. The plain R squared went up by 1%, but what that percent is not large enough to counteract this penalty.
The weighting factor. Yeah, cool.
Oh, good question. Put this in the chat. Oh. Other questions?
How did collinearity actually reduce the performance of the model? Like that's what you were saying, that
Well, it did
actually
reduce
does
it. The
worse?
adjusted R, well, no. Doesn't do worse. It just doesn't do better, which is why, which is nice that the adjusted R squareds are the same with one or two predictors, because that second predictor didn't add anything.
Enough to offset the penalty.
Yeah. Yep.
So you're saying
I
just
guess it's
collinearity, like, but why is it necessarily bad? Doesn't it just not do anything?
Because you want a parsimonious model, right? If you're
Yeah.
adding variables that are not doing anything, then it'd be better to have a simpler model.
I was reading somewhere that adding related features can help like explain confounding variables. Is that at all related to this?
So that, yeah, kind of. So when you get there are other ways to handle multicollinearity. So if you do the predictive, there's 2 predictive modeling courses. They're in the electives, although I'm pushing to make them required courses, or at least one of them required. There are other things you can do, like a principal component analysis or exploratory factor analysis, which are ways of doing dimensionality. What I'm going to say this in the technical way, and then I'll try to break it down. It's a way of reducing dimensionality. Okay, so let's take principal component analysis, which is really data specific. All I'll say that the difference, just be careful between principal component analysis and exploratory factor analysis, because the inputs and the outputs look remarkably similar. You bring in a bunch of variables and it comes out and says, well, these variables are related and this is a factor. Or you say a factor in EFA, you say a component in CFA, or I'm sorry,
PCA.
PCA. PCA. But how they get to those answers are very different. PCA is very data specific, and so is sometimes not as generalizable to new data sets. EFA is designed to be generalizable. So we use, you all took the DAX self-regulated learning assessment. The way we decided that these items grouped together and to become one kind of factor, right, which could be something like metacognition, or actually there's subcomponents, we could say planning. We actually started with just 120 items with data from a lot of students and ran an EFA, and then the output says, okay, here's the loading. So you can have, we're gonna have 6 factors, and each of these variables loads on that factor, and then we start grouping them together. So what's the output, right? So if we had a bunch of collinear variables, we could say, okay, these are all related. They might be a component if we're using PCA or as a factor for using EFA, and we just sum them to create a single variable now, right? So we take all of those correlators. So that's generally how you would handle it in a predictive model where you have lots of predictor variables. Is you might run a PCA first, figure out which variables are very closely related, and then sum them or aggregate them some way to make them a single predictor in your overall model. And you'll go in the gritty details of that in one of the upper level courses. But it's a good question, right? So that there are ways of handling it. And in data science, we tend to have a lot of predictor variables. And so that's kind of a very reasonable step. There are other things you can do. So those reduce the dimensionality in terms of variables, but then there are ways of reducing dimensionality in terms of observation. And those are things like cluster analysis or, well, that's a big one. There's another one that's name is escaping me, but it's sort of, you can imagine CFA and EFA are taking, I have a lot of columns and I want to have fewer columns. Cluster analysis is kind of, I have a lot of rows and I want to have an identifier that these rows are kind of related across a bunch of columns. But the goal is like you have high dimensional data. What I mean by high dimensional, a lot of rows and a lot of columns, and I want to reduce that to some extent, right? And collinearity is one of those ways where we, with a lot of dimensionality, these two things are correlated such that they're not going to do this. But you raise a question that I might run a little simulation. Is it possible with this penalty that adding more variables that are essentially adding zero or explaining nearly zero variance could make the R-squared, could actually make the model worse than if you just had one?
Huh.
I meant that as a question. Angela, have you thought about this? I can write a little simulation to kind of mimic that.
Right. That's a good question. I don't know.
All right. Well, that'll be my homework for next week for Thanksgiving. Right? Because if if this was zero,
Right.
right, then you increase this P, yeah, it's probably negligible, but there's probably something there. I'll check it out, but that's an interesting question. Somebody else was going to say something. I'm sorry.
I actually had a question kind of related to this. So like just in terms of like another way to think of it, could you think of like collinearity as, I mean, obviously you don't want independent variables or predictor variables that are collinear.
Mm-hmm.
Could you think of it as a way as almost like a reverse orthogonality between your inputs, and that you would want them to almost be orthogonal and that they're not actually contributing to each other, or that one is not, one can't be expressed as like a linear combination of another one? Or am I grasping at straws?
No. I mean, that's the ideal, right?
Yeah.
Ideally, you would want no overlap in all your predictors in its explanation of, and if, yeah, or if they were orthogonal, that means that would be unique contribution to your dependent variable.
Okay,
So that's the ideal.
Yeah.
You're never gonna get that, but that's what we're looking for.
Okay.
I should probably go back. I could probably rerun it. We have some small correlations, right? We could look at high school grad, and that, and what is this with high school grad and is this variable? Oh, metropolitan. So if you added, high school grad and metropolitan, that should increase the adjusted R-squared. But this GG pairs, I highly recommend. This is a useful way of kind of detecting multicollinearity. It's also a great way to summarize a lot of data all at once. And I have been known with big data sets. I mean, at home, I have a big monitor. So that's one way to do it. I used to have access to like a plotter. And when we were doing so I essentially made a poster with all the combinations and just put it up on the wall and kind of look at it. But yeah, you can create these, kind of zoom around, and it works with categorical variables, and then you can add grouping variables, which is really interesting. So you can color the points if there's sort of a grouping variable that's of interest, which is sometimes what in like experimental designs, maybe you have treatment control as a color throughout this.
The last slide you showed us where you put the LM into the ANOVA. That
Yeah.
whole exercise was just to show us how we get to the adjusted R squared, correct?
Yeah. Yes. Yeah. So the ANOVA.
I'm just thinking practically, would you need to do that for anything, or the functions already do that to find the adjusted R squared, correct?
Yes, that's correct. Yep. But if you wanted to look at, sometimes it's convenient to look at the sums of squared residuals for each component. But yeah, you're right. The the LM function and the GLM function are doing that for you automatically. So you are correct that it's done here. Yeah, I gotta fix that title. I don't know why it's truncated. Yeah, it's just done here to kind of like break it out and show how we get to that adjusted R squared.
Professor,
Mhm.
why actually R square value needs to be adjusted?
Because eventually you would just get to 1, even though you're not really adding any, additional explanation above. So you want to account for, the overlapping or, that overlapping variance.
All right.
If you didn't adjust it, eventually you would probably get to 1, and that's not really 1 or 100%.
All right. Thank you.
Again, a lot of these models and as a data scientist, this is, sort of what I think data scientists do a lot, is finding this balance between parsimony and prediction. And, in 2 weeks when I talk about those metrics, there's other ways we can evaluate this, but if you have, in my experience, parsimonious models tend to generalize better, because otherwise you're going to overfit your data, and then you got in data science, what we tend to care about is making predictions to new data sets. And if you overfit to that one particular data set, then when you go to make that new prediction, it's going to be more likely to be wrong, right? So it's a balance. There's some art to this for sure, but we often want the simplest model that explains our outcome the most.
All right, thank you.
So, Professor, if you go back one slide where you're looking at the plot with all the different
yeah, this one.
Yeah, this one, exactly, yeah. So, if you're looking at a plot like this, just visually looking at this, what would be, which direction would this drive you? If you had to just look at this and say, I can pick out these 2 or 3 different predictors that look interesting, that might explain the variability. How do you read this at a glance?
Oh, that's a good question. Often not at a glance. I usually start with the main diagonal, right? So things, I would say, oh boy, white is skewed. So right away I'm thinking, I might have to do some transformation there. This one here, what is this one? Oh, this is the female household. So I may, it looks almost bimodal, and so I often start on the main diagonal. Then I either start at the top or the bottom. I tend to see relationships really quickly, right? So this one here, what is this? I see this scatter plot, and this is high school grad and poverty. Yeah, and if I go up here, oh yeah, that is pretty highly correlated. It's not even the highest correlation though. It's this one, white, the one I picked out, right? Kind of deliberately. So I tend to look at these things like that. Now, to be honest, I start worrying about the collinearity after I run a model. I might start with everything, the kitchen sink, as I say. I'm going to put all the variables in, but then I'm going to come out and say, oh boy, here, no, it's this one, is a non-significant predictor. Okay, let's look at, and I'll come back here and say, all right, let's look at white with other variables I have, and I would probably land here and say, oh yeah, it's highly correlated here. So, you know, I probably don't need both of those. So now it comes a decision is like, well, which one do I include? And that's probably going to be predicated on my research question. Like, what am I, you know, I'm interested in modeling poverty, right? So if I'm trying to predict poverty, you know, that's a different decision than explaining, right? So saying that, you know, white and percent head of household being highly correlated takes me down a slightly different direction, right? So there's sort of this back and forth between this plot and my regression. So I might go back and then rerun my regression and drop one of them. But to be honest, sometimes I will keep them both, right? Angela, you could speak up. Like in our world, like in the education world, if you don't have a variable for social economic status, sex, ethnicity, what am I missing? You know, usually some kind of academic performance, then reviewers are going to be like, well, you're not doing it, right? Even though in our instance, sometimes those variables are not significant, but we have to keep them around because otherwise, you know, because the theory says they should be, and so them not being is of interest, and so we need to show that. So some of this is you got to know the area you're going to work in. So, you know, what I love about data science, like you guys, there's the diversity of the fields you guys are going to work in is pretty great. And, you know, some might be finance, some might be, you know, end up at like social media companies, some might be at sales companies, some might end up in education, right? And so these basic skills are the same, but how you apply them is going to be a little bit different. And so you need to know sort of the norms in that domain or context. And I can help in some areas. I have no idea in others. So.
Thanks.
Is there any specific name for this kind of plot? I mean,
yeah, it's called pairs. So there's a pairs function in base R, but this is GG pairs, which uses the ggplot framework. If I do package, oh no, you know what? Function. It's in GG Galley, I think. Is that right? Is that where, Angela? Do you remember?
I don't remember. I think this is it. But I'm not.
Well, here's an R bloggers post. Let's find out where this isn't good. You know, I could go look up my R markdown file.
Oh yeah.
Or I could do GG pairs. Yeah, it is in the G Galley package. So that's the CRAN. Oh, here's the GitHub, I guess. Let me see if this is it. So pairs plot is often, so here's, I'll put the link in the chat. Yeah, there's a lot here. I haven't looked at the documentation in a while. What's a GG matrix? Oh, right. So yeah, you can, yeah, it has functionality that you can just make your own combination of plots, and you just put subplots in. That's not the one. I tend to not use this package. There's another package that I use to do that. Two grouped. Yeah, so this is a slight variation, but you could see here we have a categorical variable. So it actually picks kind of the right things to do. But then you can tweak it. You don't have to have correlations in the upper. So with a categorical variable, correlation doesn't make a Pearson correlation doesn't make sense. You'd have to use a different correlation. But here you could say, well, let me just do box and whisker plots, right? That would be effective. Anyways, so you got the document sheet. There's a lot of options, but yeah, if you just do the GG pairs, and it doesn't take a lot of code to create it. All right.
Thank
Well,
you.
we're at 9 o'clock, so I mean, let's stick around for other questions. If not, have a fantastic Thanksgiving. We'll see you in 2 weeks. All the proposals should be graded. If you don't see your comments, reach out to us that they've been done. It should be in Blackboard. All right, we'll see you in 2 weeks.
Thank you. Happy Thanksgiving all.
Happy
Thanks.
Thanksgiving. Thank you. Happy Thanksgiving.